All right, happy Tuesday. We are in week 8 and we're starting chapter 9. We only have chapter 9 and chapter 10, so we are in the home stretch. And chapter 9 and chapter 10 have so many similarities. It's actually kind of cool how similar they are. So if you grasp chapter 9, chapter 10 shouldn't be a big stretch. So we're going to talk about, once again, obtain a point estimate for a population proportion. We did this in 8.2. So this won't be anything super weird or different. Then we're going to talk about confidence intervals. Confidence intervals include a margin of error. You've seen it in many polls where things say that this person has 37% of the vote plus or minus 4%. That's a margin of error. And we use confidence intervals with the margin of error to estimate a population. And then what we're going to do is we're going to go work backwards. So sometimes we know the margin of error we want, and we know our confidence level, how confident we want to be in our results. And we will take those numbers and we will work backwards and determine what size sample do I need in order to get me what the margin of error that I want. So we're going to do all of those things, determine our sample size, find our confidence intervals, learn what those things are, and do some math and use our fancy schmancy calculators. Love the fancy schmancies. It took me a while to start to get used to them and get into them, but once I started using them all the time, I have one on my phone. I always am using the fancy schmancies. So let's get going. Okay. All right. So we've already done a point estimate before. So when we have a statistic, so we took some sort of a poll or something, had an observation, and we know how many successes we had, and we know how many trials we had, and we will use that to get a point estimate. So we use the point estimate to estimate the population. So you take the number of successes over the sample size, and that's the point estimate. We did this in chapter 8. So hopefully it's not new information. Something weird's happened on my other computer. Just a second. There we go. All right. So Quinnipiac poll had 1,783 registered voters. They found that 1,123 were in favor of the death penalty for people convicted of murder. And so our point estimate shows that 63% of our sample favor the death penalty for persons convicted of murder. This would be our point estimate. All right. So what a confidence interval is, it's going to represent an interval that we would expect to contain a parameter. Remember that parameter is related to our population, and a statistic is related to our sample. So would say that based on our sample and the math that we did, we would expect that the um, information of our population, so like our population proportion or our population mean, we would expect it to be between these two numbers. So at the very beginning, the very first week, before y'all got to know how quirky and weird I am, did a thing about if you were walking behind someone and they dropped $100, you can keep it and nobody would know what percent of our class would keep it or what percent of our class would give it back. And I said something like between 93 and 98% of all of our students would give that back. So what I'm estimating is that out of all of the students, somewhere between 93 and 98% would give it back. I'm expecting that the actual population proportion would be in between those two values based on some math that I did. That's what a confidence interval is. So the level of confidence is I can say that I'm 99% confident that it lands in that interval, or I could be 95% confident that it'll land in that interval. So our confidence level is how confident am I? And that is, I'll explain a little bit more later on what that means. Um, actually, it's going to come up later anyway, but I'm here. I might as well say it. So if I took 100 different samples, I took 100 samples, and out of those 100 samples, like if I'm saying I'm 99% confident, 99 of those 100 would have their parameter of interest within my margin. So if I took 99 samples of our students, or 100 samples of our students, 99 out of those 100, the percent of people who would return the money would be between that 93 and 98%. So that's what the level of confidence represents. I'll get into it a little bit later with actual examples, and it's going to make it a little bit easier to understand. So this is where we are. This is what we're doing tonight. We're going to be creating our confidence intervals, and we're going to actually be interpreting them as well. This is an example. So I knew it was coming up. If 100 different confidence intervals are constructed, each based on a different sample, I would expect 95 of the intervals to contain the parameter. 5 would not contain that. So 95 of them, our population proportion or population mean or sample proportion, sample mean, 95 of them would be in that interval that we create. 5 of them would not be in there. So we're going to do some more math and it'll be easier to explain when I have actual stuff happening, actual examples. Okay. So the way that we use a confidence interval, there's two different ways. One way is to say my point estimate, so that p hat that I created, plus or minus the margin of error. So like, for example, when I said like 37%, I expect this person to get 37% of the vote, plus or minus 3%. That 3% is the margin of error. And that point estimate, that right there is it's like whatever my sample was. So I took a sample, and in my sample, 37% of those people said they were going to vote for candidate A. And so that's my point estimate. And then it'd be plus or minus that 3%. That's my margin of error. So this is one of the ways that we represent our margin of error. And I'm going to show you the other way that we represent it when we're doing the math. So our margin of error depends on three factors. Whoops. You need to have a confidence level. I will give you the confidence level. So it'll be 95%, 99%, whatever. Those are our most common. You'll see others, but those are the most common. You need a sample size. So as my sample size gets larger, the margin of error is going to get smaller. Because I'm taking a bigger chunk of the population, I can expect that error to be less. So bigger chunks of the population, smaller margin of error. Standard deviation. So if I have a very large standard deviation, the population is going to be spread out, and that interval is also going to be spread out. So my interval is going to be dependent on that. If I have a super small standard deviation, my interval of my confidence interval is going to be smaller. I'll give you a second to write things down, and we'll move on. Okay, so remember, back in 8.2, I gave you this right here, standard deviation. I gave you this standard deviation for sampling distributions. We are going to be using this for our margins of error as well. We also need to remember this. So the NP times 1 minus P greater than or equal to 10, that represents whether or not our population is normal. So whether our sample size is big enough actually to make our sampling distribution normal. That's what I meant. If our sample size is big enough, then our sampling distribution becomes normal. This is what determines if it's big enough. And each trial needs to be independent. This 5% rule applies. So our sample size can't be more than 5% of the population. All of this still applies. We're taking stuff from 8.2 and applying it here. But this is the standard deviation that we're going to be using in our margin of error calculations. And still, our mean is going to be whatever our population proportion is estimated to be. We're going to use that as our mean. All right. So this is how we calculate our confidence interval. So I hate that that keeps happening. Okay. So what we do is we take our p hat, so our point estimate, and we're going to determine, based on our level of confidence, we're going to determine how many standard deviations we can be away from the mean and still be in our, or the p hat or mean, and still be within our confidence interval. So if I was 95%, I don't remember the numbers, so we're going to get a certain Z score, which is called a critical value. Is that what we're calling it? I think that's what we're calling it. Yeah, sorry. I couldn't remember if we called it that yet. So we're going to get a critical value. The critical value means that's the edge of my confidence interval. That's how many standard deviations I can be away from my mean and still be in the confidence interval. That's going to be the edges. We're going to get a Z score. You take that Z score, which is the critical value. I'm going to put an arrow here. Critical value. I take that critical value and I multiply it by the new standard deviation so that I can get the actual data value or the distance, the actual percent, because this is population proportion. So I want to get the value of the top and the bottom of my confidence level. So what I'm doing here, I'm going to draw a picture because pictures help. So this is my confidence interval. And let's say that I'm doing a 95% confidence interval. So this is 95% right here. Now we are not using the empirical rule for 95%. We're using the actual Z scores. So we're going to get a Z value. We're going to get a Z score. So this is 2.5%. And this is 2.5%. I'm just trying to remind you, since this is the center, that's what this means right here. The alpha is the difference between 100% and the 95%, or whatever my confidence level is. And so I cut that in half and I find the Z score that works with that. Okay. So 95% confidence interval, this right here is 97.5, and this right here is 0.25. Do you vaguely remember this from previous chapters where we split that in half? So I need to find the Z score that goes with the 97.5% mark. That's where my critical value is going to be. Then I multiply that by the standard deviation that gives me the margin of error. Once I'm doing this with numbers, it's going to make a lot more sense. So let's do one of those examples. First, this is the exact same picture I just did, and critical value. I took this from your book. I don't know if you can tell. I took a picture of your book, and because I really liked this diagram, which is basically the diagram I just drew. All right. So the bottom of our Z table, I don't really like this one, but I'm going to show you this and then I'll show you ours. At the bottom of the Z table, it shows your level of confidence. Oh, that's ugly. The level of confidence. It shows you what the area is in each tail. So 95% confidence, I have 2.5%. I have 2.5% in each tail because I had to cut that in half. And it gives me a critical value of 1.96. So that is the Z score that I'm going to use to multiply by the standard deviation. This just gives you a few of them. I'm going to show you on our Z table. This is our Z table. It gives you a few of them. This one gives you 90, 95, 98, and 99. So this gives you the most common ones. Now, for example, let's say that I was doing a confidence interval and it wanted something weird like 85%. Let's say that it wants 85% confidence interval. I don't have that. It doesn't give it to me. So I'm going to have to use inverse norm. So I take 1 minus 0.85. This is going to give me 0.15. All right. So I'm going to divide this by 2 because I need the area in both of the tails. I'm going to divide it by 2. So this is 0.075. This right here is the area in the tails. And I'm going to use inverse norm to find my z-score. Now we need to use the positive. It's going to give you a negative z-score. We should be using the positive, but this is, you can get at least get the right number. So once I put this in my calculator, 0.07501 gives me a z-score of negative 1.44. And so I just need to make it positive. So I'm going to use 1.44 would be, this would be the critical value I would use. Once again, this is going to be a lot easier when we're doing an actual example. But if they don't give it to you right here, if they don't give you a confidence level right here, or the critical value, then just use your inverse norm on your calculator for the center. Okay, let's do an actual example. I think I have one here in a second. I'm going to leave this right here. We're going to talk about it in a minute. All right. So in July of 2008, a Quinnipiac University poll asked, oh, I hate when I do that. Sorry about that. Asked 1,783 registered voters whether they favored or opposed the death penalty for persons convicted of murder. 1123 were in favor. Okay, we're going to obtain a 90% confidence interval, but first I'm going to test my things. 1783 is definitely less than 5% of the entire population or entire voters. I'm not even going to write that down. It is definitely less than 5%. So NP, my P hat, 1123 over 1783. I think we've determined that that was 63%. Yeah, 0.63. So what I'm going to do is N is 1783.63, 1 minus 0.63. And all I need to determine is that that's greater than or equal to 10. Let me see here. So 1783 times 0.63 times 1 minus 0.63. Oh man, that number is a lot larger than, oh, that's because I forgot a decimal. Like, man, that's crazy. That's so big. Yeah, decimals are your friend. There you go. It's still bigger. This is 415, so that is greater than or equal to 10. So we're good. Okay. So now what I'm going to do first, is I'm going to find the margin of error. This is the p hat. So this is just going to hang out here. So my margin of error is going to be the critical value times my sigma sub p hat times my standard deviation. This is a 90% confidence interval. So let's bop on over to our t table, or sorry, our z table. Oops, it's on my, okay. It is on my computer. Let's pop on over here. So at a 90% confidence interval, my critical value is 1.645. I do not know why at 90% and 99% they go to 3 decimal places. I have no idea why, but they do. So I'm going to use 1.645. Okay. And I'm going to multiply that by the standard deviation. So remember, it's p times 1 minus p. So it would be 0.63 times 1 minus 0.63 divided by my sample size. Ah, sorry about that. I set it on my lap, and when it flips upside down on my screen, I can turn that off. Let me just turn that off. There we go. Now it won't flip. All right. So now I'm going to multiply this on my calculator. Mhm. Typos are my friend, apparently. So I got approximately 0 point, let's just do 0.02. Let me know if I mathed wrong, please. Okay, so this right here is my margin of error. So I have a 2% margin of error based on my sample size and my confidence level. So what I can say is my confidence interval, 0 point, let's see here, confidence interval, I'm going to write it right here, is p hat, 0.63 plus or minus 0.02. I'm not going to get mad at you if you said 63% plus or minus 2%. Nobody's going to get mad at you for that. The other way that we write this is you actually do the math. So I would take the 0.63 plus 0.02, and I would do 0.63 minus 0.02. That gives me the edges of my confidence interval, and I would show it like this. So the conclusion that I would write, so I would say we are 90% confident that the actual proportion of people who believe that or who are in favor of the death penalty for persons convicted of murder is between 61 and 65%. Or you can say is 63% plus or minus 2%. Questions before I move on? I know it's a lot. I'm going to give you a calculator function also. Okay, let me pop over here. So here's it typed out. Oh, where things are disappeared. Things are missing. I don't know why all of the math is missing. Sometimes it just does that. I don't understand. So we saw it on the other screen, and I think that the PowerPoint that I have, I don't know why it's missing. That's really strange. My numbers are here. So here's their interpretation. We are 90% confident that the proportion of registered voters who are in favor of the death penalty for those convicted of murder is between 61 and 65%. We're going to do another example. Questions before I move on? All right. Don't do this yet. I don't want you to do this yet. I'll give you that in a minute. Okay. I'm magic. Don't do that yet. Okay. We'll do the calculator in a minute. Okay. The Gallup organization conducted a poll in which a simple random sample of 1,016 Americans 18 and older were asked, do you consider the amount of federal income tax you have to pay is fair? Of 1,016 adults, 558 said yes. So we're going to get our p hat. Make this smaller. Okay, my p hat is going to be 558 over 1,016. So this is about, we're going to call it 55%. So that's my p hat. The next thing I want to get, let's get my critical value. The reason it's alpha divided by 2 is because we're looking at the center. And when we're dealing with the center, it's half of what's left is in each tail. That's why it's alpha divided by 2. So we're looking at a 95% confidence interval. So I'm going to jump back to my Z table. 95% confidence interval gives me 1.96 as my critical value. So that's my Z sub alpha divided by 2. And I'm going to calculate the standard deviation. I'm doing it kind of slightly different than I did last time. I'm doing each of them separate just because I kind of want you to see each calculation separate. So here I'm going to do 0.55 is 1 minus 0.55 divided by my sample size, which is 1016. Okay, 0.55. All right, this is about 0.0. I'm out of room. Let me move things over. It's a nice thing about having a fancy. Okay, let me just make it a different color then if it's gonna encroach. Okay. So 0.016, that's what I'm gonna write. That's a different color, but it'll live. Okay, so this would be my standard deviation. So remember, the way that we're going to write our margin of error, my margin of error is going to be my z sub alpha divided by 2 times my standard deviation. So it's 1.96 times 0.016. This is going to give me my margin of error. About 0.03. I'm going to make sure y'all got the same number I did before I move on. All right. This is the margin of error. This is what we're going to use for our confidence interval. So it's about a 3% margin of error. So two different ways I can write it. Remember, we either write it as p hat plus or minus my margin of error, or we do p hat plus my margin of error, or what's minus? What the heck? We do a parenthesis with p hat minus margin of error, comma, p hat plus margin of error. These are the two different ways that we represent our confidence interval. So I'll write it both ways here. I have 0.55 plus or minus 0.03, or 0.52, comma, 0.58. So I would state the actual proportion of adult Americans who believe that the amount of income tax that they pay is fair is between 52 and 58%. Or I could say it's 55 plus or minus 0 or 3%. Or you could say 0.55 plus or minus 0.03. Either way. Questions on this? It's like a fancy calculator function. I will give that to you. Come on. There it is. I'm going to have to delete some of this stuff or move it and move this so that it's out of the way. Right down there. Our calculator function, close to this. It's right here. This is our calculator function. It's one prop z interval, one proportion z interval. We're going to put this in there and see how close we get to our numbers. So let's pop over to our fancy schmancy calculator. I have so much stuff in there. There we go. All right. So you're going to go to stat and then arrow over until you get to tests. So it's 2 over. So stat tests, and you need one prop z interval. So one proportion z interval. So it's letter A. So stat tests, and then go down to A to get to one prop z interval. And give it a second. They're all there. We're going to hit enter. All right. So your X is your number of successes, which was 558. Your N is your sample size. That was 1,016. My confidence level was 95%, so put in 0.95. So successes, sample size, confidence level. Go down to calculate and hit enter. Okay, what this gives me, it will not give you the actual margin of error, but it does give you the bottom and the top of your confidence interval. So I have the lower and the upper, and mine was 52 to 0.52 to 0.58, which is absolutely correct. And when we round these numbers, we get there. But it also gives me the p hat right here. So if you needed to find the margin of error, you could just take this top number, subtract the p hat from it, and that would give you your margin of error. So I'll do this on my other screen. So I would do, that was, let me see here, put zero, I'm going to take the numbers 0.57981. I know those numbers are a lot more than I used. 0.5492. Okay. So I'll do this up at the top of my screen. I'm just going to subtract those numbers from each other. Uh-oh. 5492. Imagine that. I got 0.03061. I would round that to 0.03 and we're good. So you just take the top of your confidence interval, subtract the p hat, and then you're good to go. That gives you your margin of error. Questions before I move on? All right. Pop over to the next screen, maybe. I already said this. So they will, many times they'll just use a capital E for margin of error instead of the ME that I use. They'll just use the capital E. And this is just your margin of error. I already did this. I kind of incorporate the whole thing earlier. So it's just your critical value times the standard deviation. So sometimes we want a specific margin of error. I want to know, I want my confidence, my margin of error to be 2%. I want my margin of error to be 3%. So if you take too small of a sample size, your margin of error is going to be super large. And if I said that they're getting 37% of the vote plus or minus 15%, you'd be like, why am I even bothering to look at this poll? I want a super small margin of error. I want my poll to be believable, my answers to be believable. So using this formula, it's pretty easy to figure out a good sample size to use. So I can figure out I want a margin of error of 2%. Use this formula to determine what size sample size I need to get a 2% margin of error. The problem with this formula, though, is it uses p hat. So all I did was took this formula right here and I used algebra to solve for n. That's all I did to get this. I just solved for n with the margin of error formula, just solved for a different variable. But the problem is I need to have a sample size to figure out to get p hat. But we need to find the sample size. So instead of using a p hat, because we don't have one of those, we have two different options. And I'm going to pop to the other screen for that. We can either look at a different study. So someone else may have done a study just like it previously. We can look at somebody else's study and get kind of an idea based on theirs what p hat we can use. And it's going to get us in a good enough ballpark to use our margin of error that we want. If there was no previous study, we are going to use 0.5 for p hat. So using 0.5 gives us the largest possible value for our sample size. So you either use a previous study, which is what we prefer, or you can use 0.5. Either one of those is fine. And that's going to get us there with our formula. Let's do some examples. Okay. So one thing important to note, you always round up to the next highest integer. You always round up to the next highest. And I like to use the example of, so let's say that I'm taking a bunch of kids on a field trip. Maximum capacity on each bus is 50 kids. It's just a number I pulled out of the sky. Maximum number of kids on each bus is 50 kids. We cannot put more than 50 kids on the bus. Just can't. I am taking 203 kids on this field trip. I cannot shove those 3 kids into the other buses. I have to get a 5th bus. I just have to. I cannot round down. I need to round up. I need to have that 5th bus. And so, for example, if I solved for sample size and I got 105.2, 105 isn't enough. I have to use 106. Always round up. Always. And always round to an integer because I can't sample 105.2 people. I have to sample 106 people. So you can't sample a partial person. Okay, let's do some math. Let's just do this. Okay. A sociologist wanted to determine the percentage of residents of America that only speak English at home. We need to find the sample size that we need to estimate within 3 percentage points with a 90% confidence interval. We're assuming that we're going to use a 2000 estimate from a census of 82.4%. So I have a previous estimate. All right. My formula, n equals p times 1 minus p times z sub alpha divided by 2 over n. I sure hope that that's the formula. Yeah. Over not n, over our margin of error squared. This is my formula. My p hat. This is the p hat. So n equals, my p hat is 0.824 times 1 minus 0.824. I need my critical value for 90%. Pop over to my, pop over here, 90%, 1.645. 1.645 is my 90%, so I'm going to use that. Margin of error is 3 percentage points, 0.03. Do not forget to put it into a decimal. If you're careful with your parentheses, you can put this entire thing into your calculator. Let's do this. Whoa, I got 436.04. Please check my math. I'm going to give you a second. Let me know if you got something different. All right. We need a sample size. That's a Z. Of 437. Yes, that is barely over 436, but 436 won't work. You always round up. I need 437 people, households, I guess, sampled. Questions before I move on? All right. Here it is all typed out pretty. The sociologist must survey 437 randomly selected American residents. We have one more slide, one more example. We got this. Right. So, an economist wants to know if the proportion of US population who commutes to work via carpooling is on the rise. We want to know what sample to obtain if they want to estimate within 2 percentage points of the true proportion with 90% confidence using a 10%, a previous survey of 10%. So remember from back here, our z-score for 90%, our critical value, is what was it? 1.645? Yes. And our formula, that's really ugly. Okay. I would like you to get started ahead of me. I'm going to fix my Z because it's ugly. Go ahead and get started ahead of me. You have the same number as me? Okay, good. I worry sometimes. My calculator skills sometimes leave something to be desired. So the next question says, what if the economist didn't use any prior estimates? So remember, if we don't have a prior estimate, we're just going to use 0.5. So it's going to look like this. One minus 0.5 is also 0.5. But previously, if I didn't do the one minus, I confused people. A lot of that is because it's a night class, and I think many of us don't have full brain cell power this late at night. I know I don't. So it's it happens. So this is if they didn't use a prior estimate. You're going to see there's a big difference in the number that we have to survey. A huge difference, isn't it? It's, yep, good job. Yeah, so we definitely, you definitely, if you can find a prior example, it's a good idea to use that. It's, that I've seen some final projects that people have used confidence intervals and they'll just like Google. Sometimes they'll just be like, if, I guess AI exists now. You can use a prior estimate from something like that and say, well, I should have taken a sample of this size. So some people have done that where they say, I sampled 50, and so I got this confidence interval. If I wanted to get a confidence interval or a margin of error of 0.03, I would have needed to sample this many. People have thrown all sorts of interesting things in their final projects. You are not required to do anything with confidence intervals in your final project. Just letting you know some people have in the past. And they've used this saying, this is how many I should have if I wanted this particular sample size. It's happened. Any questions before we move on? I have one more thing I want to talk about with the homework, kind of to help you be able to use your calculator. Other than that, this is the last slide. So questions? All right. So in our calculator, we have to have the number of successes and we have to have the sample size. Sometimes my open math it gets tricky with us. I really intended to already be in my open math, but it didn't happen. Okay. So in our homework, 9.1 homework, let's get in here. And then 9.1 homework. Sometimes instead of giving you, they'll give you this, instead of giving you the number of successes, they'll give you a percent. Then when you put that in your calculator and you say, okay, what's 83% of 590? So when I put in 83% of 590, I got 489.7. Now, the calculator's not going to like that. For your number of successes, we can't have a decimal. So most of the time, if you just round to the nearest whole number, it'll get you there. So for this one, 489.7, if I use 490, my calculator should be fine. It should be happy with me. I'm going to do that right now to see if it happens. Let's see. So I'm going to do stat, go over to tests, go down here. Okay. So it wants to know number of successes. I'm going to go 490 because I have 489.7. That's closer to 490. My sample size is 590 and my confidence level was 95%. Let's see here. So it gives me 0.80 and 0.86. Let's see if it likes it. Oh, it wanted to know my margin of error. Okay, well, let's go back to here. I mean, it works because 0.83 is my p hat. So 0.86 is 3% above and 0.8 is 3% below. So that did give me the proper margin of error. So once again, what I did did 0.83 times the sample size because it said 83% of the sample size had this characteristic. So it gave me 489.7. If you round to the nearest whole number, almost every time it'll work fine in your calculator that way. I'd do 490. Almost every time it's going to give you the correct answers for here. Every once in a while it doesn't. So then you would just have to go and do it manually. But you didn't lose much time by trying the calculator. You just lost a few seconds. And I encourage you to use your calculator. All right. So that's all I have for you. Are there we'll do the lab on Thursday. Any questions for on the recording? All right, let me turn off the recording.